but NASA has just announced an amazing discovery.
By 2035, you could check into a house on the moon. Not a sci-fi movie set, not a simulator, a real, sealed, radiation-shielded home with electricity, water recycling, and maybe even a view of Earth from your bedroom window. NASA's not just talking about going back to the moon, they're talking about staying. The question isn't if we can do it, it's how you build a neighborhood in a place with no air, no rain, and deadly dust. The problem and ambition. For decades, lunar missions were nothing more than brief, spectacular visits, quick stopovers in the vast black of space. The Apollo astronauts touched down, spent a few days bouncing around in low gravity, planted a flag, snapped some iconic photos, and scooped up a few hundred kilograms of moon rock. And then they headed home. It was exploration in its purest form, bold, daring, and temporary. But exploration is no longer enough. NASA's ambitions have evolved. Now it's not about going to the moon, it's about living there. The difference is enormous. Why the moon? Because it's the most logical launch pad for humanity's deeper journeys. It sits a mere 384,000 kilometers away, close enough to reach in about 3 days, far enough to teach us how to survive away from Earth. It holds resources like water ice locked in shadowed craters, which could be turned into drinking water, breathable oxygen, or even rocket fuel.
Very few people would have expected water of any particular substance to be available on the sunlit side of the moon. And the main reason for that is because the intense ultraviolet radiation from the sun actually would break down that water.
It offers the perfect test bed for technologies that will one day sustain crews on Mars, where the stakes and the distance will be far greater. But here's the catch. Surviving on the moon isn't about sending another rover or lander. It's about building a home. A place where people can work, sleep, eat, and stay safe from the temperature swings of 127 degrees Celsius plus in sunlight to minus 173 degrees Celsius in darkness. We'll need power systems that never shut down, labs for research and manufacturing, habitats that can handle decades of radiation, dust, and micrometeorites. The goal is clear. The technology is advancing, and the clock is already ticking toward 2035, the year NASA envisions its first permanent lunar base taking shape. Artemis and beyond. At the heart of NASA's lunar ambitions is the Artemis program, a multi-mission roadmap designed to return humans to the moon and keep them there. It's not just one launch or one landing. It's a step-by-step buildup of capability, each mission laying the foundation for the next. Artemis 1 launched in 2022. Was the crucial shakedown cruise, an uncrewed flight that put the brand new Space Launch System, or SLS, and Orion's spacecraft through their paces. It was about proving that the hardware could survive the deep space gauntlet and bring a crew home safely. Artemis 2, set for 2025, will be the first crewed lunar flyby since the Apollo era. No landing yet, just a high-stakes rehearsal in which astronauts orbit the moon, test life support systems, and make sure everything works under real conditions. Artemis 3, slated for the late 2020s, is where things get historic. Astronauts will set foot on the lunar South Pole, a region no human has ever explored, rich in shadowed craters that may hide vast reserves of water ice. And then comes the big leap, the Artemis Base Camp in the 2030s. A semi-permanent outpost with labs, living quarters, and exploration gear. The plan is to start modestly, with mobile habitats and pressurized rovers, and then grow into fixed housing modules that can weather decades of lunar extremes. NASA isn't going it alone. Private companies are woven into the blueprint. SpaceX will ferry cargo and crew with Starship. Icon will use giant 3D printers to turn lunar dust, regolith, into strong, radiation-shielding walls. Even architectural firms like Big are designing futuristic shelters fit for another world. How you build on the moon. Here's the first big problem with lunar construction. You can't just ship up lumber, drywall, and a few bags of cement. Every single kilogram launched from Earth costs thousands of dollars in fuel and logistics, meaning that sending a prefabricated house to the moon would have a price tag somewhere between astronomical and don't even ask. The solution is simple in concept, but radical in execution. Build with what's already there. This approach is called in situ resource utilization, or ISRU, using the moon's materials to create habitats, roads, landing pads, and even tools. That means 3D printing with lunar regolith, the fine powdery dust that covers the moon's surface. It's not pleasant stuff. It's sharp, clingy, and gets everywhere. But with the right tech, it can be turned into a sturdy, concrete-like material. Other techniques include sintering regolith into solid bricks using concentrated sunlight or high-powered microwaves, essentially baking building blocks out of dust. Water ice, locked in permanently shadowed craters, can be melted into drinking water or split into oxygen for breathing and hydrogen for rocket fuel. The moon's soil is also laced with metals like aluminum and titanium, which could be extracted for structural parts or machinery. NASA's Project Olympus, spearheaded by ICON, is bringing this vision into reality. They're developing massive, autonomous 3D printers that can operate in the vacuum, radiation, and extreme cold of the lunar surface, layering molten regolith into walls, domes, and shelters without a single human swinging a hammer. On the moon, your construction crew won't be carpenters in hard hats. It'll be robots under a pitch-black sky, patiently printing humanity's first off-world neighborhood. Key takeaway number 1. Every kilogram from Earth costs a fortune. Here's the brutal truth about space construction. Weight is the enemy of your budget. Launching anything from Earth, whether it's a beam of steel, a bag of cement, or a box of screws, costs thousands of dollars per kilogram. And the higher the weight, the higher the fuel requirements. The bigger the rocket, the more complex the mission, and the more your bank account starts to look like a crater. This is why every serious lunar habitat proposal starts with one core principle. If you can make it there, make it there. It's not just about saving money, it's about making the mission possible at all. For perspective, shipping a single bag of concrete to the moon would cost millions of dollars. Millions! And when you factor in the sheer volume of material needed for even a modest base, you quickly see why flying up Earth-made houses isn't just impractical, it's absurd. The moon, on the other hand, comes with its raw material supply chain already in place. Lunar regolith, that dusty, clingy, powder-like surface layer, is everywhere. It's abrasive, it's electrostatically charged. It's a little nasty to handle, but it's free. No rockets required. The challenge isn't getting the material, it's taming it. Processing lunar dust into bricks, beams, and panels takes clever engineering and specialized equipment that can operate in an environment where there's no atmosphere, no rain, and no margin for error. The builders who thrive on the moon will be the ones who think like survivalists, making use of whatever's at hand, adapting to what the environment offers, and treating every Earth shipment like a precious luxury item. Early prototypes. The moon may still be untouched by bulldozers and construction cranes, but here on Earth, the first test runs of lunar building are already underway. ICO, the company leading NASA's Project Olympus, has been experimenting with regolith simulant, a specially engineered stand-in for real moon dust. They've 3D printed walls, arches, and dome sections that mimic the texture, density, and strength of what future lunar habitats might require. Every layer laid by these printers is a step toward proving that automated construction can work in the harshest environments imaginable. Meanwhile, BIG, the Bjarke Ingels Group, is bringing architectural artistry to the challenge. Their designs feature sweeping domes and rounded structures, all covered in thick layers of regolith shielding. This isn't just an aesthetic choice. On the moon, that extra material is life-saving armor against constant radiation from the sun and the occasional micrometeorite that could otherwise punch through a habitat's thin shell. NASA, for its part, has turned the problem into a global competition. The 3D printed habitat challenge invited engineers, architects, and dreamers from around the world to design and build full-scale prototypes using regolith simulants. The results were stunning, from squat, bundle-like modules to elegant, interconnected domes, all created with the same basic premise: use the dirt beneath your feet to survive. These prototypes aren't just pretty concept art brought to life, they're functional test beds. They're where engineers refine printer nozzles, test material strength, simulate lunar temperature swings, and figure out how to keep dust from clogging every moving part. What we're seeing now is the rehearsal before the curtain rises, the small-scale, earth-bound trials that will shape humanity's first real neighborhood beyond our planet. Key takeaway number 2: moon dust isn't just dirt. At first glance, lunar regolith looks like harmless gray sand, the kind of stuff you might sweep up off your porch without thinking twice. But under a microscope, it's a different story entirely. The grains aren't rounded like Earth's beach sand. They're jagged, sharp, and abrasive, more like powdered glass than soil. And because the moon has no wind or water to erode them over billions of years, each tiny particle is a miniature weapon, clinging to spacesuits, scratching visors, and grinding away at seals and joints. During the Apollo missions, astronauts discovered just how nasty it can be. The dust clung to their gloves, got into the lunar module, and even irritated their lungs. Left unmanaged, it's a maintenance nightmare. And yet hidden in those razor-edged grains is a treasure trove of building material. Lunar regolith is rich in oxides and metals: aluminum, titanium, silicon, and iron, all essential ingredients for construction. With the right technology, you can heat it until the particles fuse, creating a dense, rock-like material that's incredibly strong. This process, called sintering, turns a hazard into a structural asset. Now add robotic automation to the mix. Imagine fleets of autonomous 3D printers, each melting and stacking regolith layer by layer, churning out walls, tiles, and even landing pads. No cargo ships, no lumber yards, just the raw surface of the moon transformed into infrastructure. It's the ultimate irony. The very thing that once threatened astronauts' safety could become the foundation of our first lunar settlements. The moon's most persistent hazard might also be its most valuable resource. The science. Designing a home on the moon isn't like building a house on Earth. It's more like building a tiny spaceship and then burying it in rock. Every habitat must tackle 3 relentless technical challenges, each one capable of ending a mission if underestimated. First, radiation. Without an atmosphere or magnetic field, the moon sits naked under a constant barrage of solar particles and cosmic rays. Over time, exposure isn't just dangerous, it's deadly. That's why lunar habitats will need walls at least 2 to 3 meters thick, packed with regolith for shielding. It's not about comfort, it's about survival. Second, thermal extremes. On the moon, hot and cold take on a whole new meaning. When the sun is up, surface temperatures can soar to 127 degrees Celsius, hot enough to boil water. Just 2 weeks later, during lunar night, the temperature can plummet to minus 173 degrees Celsius, colder than liquid nitrogen. Any structure has to endure these wild swings without cracking, warping, or becoming brittle. Third, vacuum and dust. The moon's near-perfect vacuum means habitats must be airtight, with materials that don't outgas or degrade in the absence of air. And then there's the dust. Sharp, clingy, and relentless. It gets into machinery, gums up joints, and can damage human lungs if inhaled. Put it all together, and you start to see the reality. A lunar house is far closer to a life-supporting spacecraft than a suburban bungalow. It needs pressure shells, radiation shielding, advanced climate control, and dust mitigation systems, all anchored securely to bedrock, so a micrometeorite impact or thermal shift doesn't undo months of work. The dangers. Life on the moon comes with a list of hazards that would make any Earth-based architect sweat. Out there, safety isn't just a design priority. It's a constant battle against an environment that does not want you to exist. Take moonquakes. Yes, they're real, caused by tidal stresses from Earth's gravity. Some can last for several minutes. They're not as violent as big earthquakes, but in a place where your walls are also your life support. Even a small shift in the ground can be serious. Lunar habitats must be anchored deep and built with shapes that distribute stress evenly. Think rounded domes rather than boxy corners. Then there are micrometeorites, space pebbles smaller than a grain of rice, but traveling at speeds of up to 60,000 kilometers per hour. At that velocity, even a speck can punch through thin metal. The answer? Layered shells, with outer walls designed to absorb and disperse impact energy before it reaches the pressurized interior. And we can't forget dust infiltration. Lunar regolith doesn't just get everywhere, it clings like it's alive. It rides in on spacesuits, floats in the airlock, and settles into crevices where it can grind gears, clog filters, and even pose a health hazard if inhaled. Engineers are designing airlocks with built-in dust traps, magnetic filters, and suit port systems to keep the stuff outside where it belongs. Each of these threats dictates the design choice from wall thickness to door seals, from air system redundancy to the curvature of the roof. On the moon, safe isn't a final state you achieve. It's a daily engineering challenge you never stop meeting. Key takeaway number 3. Building for survival changes the idea of home. On Earth, we build homes to be welcoming, spaces that reflect personal taste, comfort, and style. We choose colors for mood, arrange windows for sunlight, and plant gardens for beauty. But on the moon, all of that takes a backseat to one priority: staying alive. Survival dictates every design decision. Thick walls aren't just for insulation, they're armor against radiation, temperature extremes, and micrometeorite strikes. Instead of large glass windows with scenic views, you'll have tiny portholes, or more likely, high-definition screens displaying the outside world from cameras. A real window would be both a weak point and an invitation for thermal loss. Even the concept of rooms changes. Some habitats may be built entirely underground or buried beneath meters of regolith to maximize shielding. Interiors will be sealed, pressurized, and climate-controlled, with every cubic meter carefully managed for efficiency. Air, water, and temperature aren't just amenities, they're systems that must run flawlessly, 24/7. And yet, within those constraints, comfort will still find a way in. LED lighting can mimic natural daylight. Walls can be decorated with personal mementos or digital art. Furniture will be compact, multifunctional, and often built into the structure itself to save space. The lunar home of 2035 won't have a white picket fence or a backyard. It won't look like anything from a suburban neighborhood, but it will be safe, functional, and most importantly, sustainable. Every detail will be a step towards something far bigger, proving that humanity can create not just a foothold, but a lasting presence off-world. The 2035 vision. By 2035, NASA's blueprint for the moon transforms from concept art into reality. Artemis Base Camp, humanity's first semi-permanent outpost beyond Earth, could be a small but thriving hub of science, engineering, and exploration. Multiple pressurized habitats will dot the lunar surface, each one a self-contained life support bubble. Some will serve as living quarters, others as labs for geology, chemistry, and biology experiments, all connected by covered walkways or rover paths. Power will come from a network of solar arrays spread across sunlit ridges, paired with advanced energy storage systems to bridge the 2-week-long lunar night. Every watt will be managed carefully, ensuring that life support, communications, and research never miss a beat. Greenhouses will provide fresh produce in controlled environments, not just supplementing food supplies, but boosting crew morale. Imagine astronauts harvesting lettuce or tomatoes, while just outside, the surface lies barren and airless. Infrastructure will extend beyond living spaces. Landing pads and rover garages, 3D printed from regolith, will handle the constant traffic of cargo and crew vehicles. These hardened surfaces will protect habitats from the dust clouds stirred up by rocket landings. And there may even be room for something unexpected: tourism. Short-term civilian stays, housed in dedicated visitor modules, could become both a public engagement tool and a source of funding for further exploration. From orbit, the base will appear as a cluster of glowing domes under starlight, a tiny human oasis in a sea of gray dust. On the surface, it will feel both alien and oddly familiar, a place built for survival, yet slowly adapting for comfort. It will be more than just a moon base. It will be the first step toward a permanent human presence beyond Earth. In just over a decade, humans could be living full-time on the moon, sleeping, eating, and working under a sky that never changes, with Earth as the constant view in the distance. The technology is ready. The funding is in motion. The vision is clear. So the real question isn't if NASA can build houses on the moon. It's, when will you be ready to move in? Subscribe for more stories about the future being built right now, and tell us in the comments, would you spend a month living on the moon if you could? Stay blessed and stay curious.